Hello guys, once again, it's Noel with another chemistry video. Today we're going over lattice enthalpy and Born Haber cycles, which is in OCR A 5.2.1 to 5.2.3. So today we're going to have some learning objectives, as we always do. One of them, you will understand that by the end of this video you should be able to demonstrate and apply your knowledge and understanding of the use of lattice enthalpy of a simple ionic solid such as NaCl or MgCl2, and relevant energy terms for either the construction of Born Haber cycles or related calculations, which we'll go through both. Also, we're going to understand the explanation of the term lattice enthalpy, which is also there, but we will go through it later on, and use as a measure of the strength of ionic bonding in a giant ionic lattice. We will also go through use of the lattice enthalpy of a simple ionic solid such as NaCl and MgCl2, and relevant energy terms for the construction of Born Haber cycles, as said before. So now let us begin. Lattice enthalpy. This is when we have oppositely charged ions which are attracted to each other, forming a lattice. Forming these ions require a lot of energy, but once formed, they allow a lowering energy to form the lattice, which normally compensates to the huge amount of energy needed to actually form it in the first place. Now, you'll find more about this in 2.2.4, but this is more about the basic ionic compounds. But I suggest you do read that as well, because it will help. Now let's carry on. Now, the above reactions explain why ionic substances are very strong ionic bonds, and why they have high melting and boiling points. So now, to measure this all out, actually, we have this specific thing called lattice enthalpy. Lattice enthalpy is the enthalpy change that accompanies the formation of 1 mole of an ionic lattice from its gaseous ions under standard conditions. Now, with that known, let's talk about bond strengths. Lattice enthalpy values can show the strength of a bond. More exothermic values indicate, firstly, that stronger ionic bonds or greater electrostatic interactions. Secondly, that higher melting and boiling points due to more energy required to overcome interactions. Lastly, we know that most exothermic lattice enthalpies come from small ions with large charges, as they can get closer and cause larger electrostatic forces. So now, let's move on to the main part of this whole topic, Born Haber cycles. As stated in the last video, which you should watch as this will prepare you the best for this video, some equations show that is not possible. Lattice enthalpy is actually impossible to find directly, therefore we will have to find it indirectly. The way we do this is via Born Haber cycles. Now, Born Haber cycles have many steps to it. We have the standard enthalpy change of formation, which you should have known from previous topics such as enthalpy cycles. The standard enthalpy change of atomization, this is new, this is in this topic. First ionization energy, which is year 1 topic again. The second ionization energy, year 1 topic again. The first electron affinity, which is year 2 topic. The second electron affinity, which is also year 2 topic. And now, with all these, we're going to go through an example question to help you actually understand what's the purpose of these in the Born Haber cycle. So, let us look at an example question right now. The table shows the enthalpy changes needed to construct a Born Haber cycle for sodium oxide, which is also known as Na2O. So now we have different energy calculations. So the first ionization energy of sodium produces an enthalpy change of positive 495. If you want, let us actually underline all of these so this helps. So the keyword here is first ionization and 495. Now let's look at the second term we have. First electron affinity, which we also know is a very key for the Born Haber cycle. which gives us minus 141. Next one we have is second electron affinity, which gives us 791. We also have enthalpy change of formation, which is a year 1 topic, which you guys should know hopefully, which is minus 416. We also have enthalpy change of atomization, which we also discussed, and we will further discuss, which has 109. And we have again the enthalpy change of atomization. That's not the best color, is it now? Which is 247. Now let's actually look what the question asks us. Use the enthalpy table, which is this one that we just used, to complete the Born Haber cycle, which is this. By putting in the correct numerical values on the appropriate dotted lines. So firstly, let's talk about what we actually have. So as I was telling you before, we cannot have a direct route to how to solve this. What they want to find is this very long line that goes all the way down to make Na2O, as it says. So now the problem is we can't make this from these values here. In order to do that, we have to go through a very long process, as you can see. If I show you right now, we have to go through all of this to get our basic Na2O. So now we have 1 stage, 2 stage, 3 stage, 4 stage, 5 stage, 6 stages. Now if we look previously, we have 1, 2, 3, 4, 5, 6 stages as well. So now we have to use all of these definitions to form ourselves a Born Haber cycle. So let's start with this. We see that we have, oopsie daisies guys, okay, we have Na2O. Okay, so we have to connect this value to something. What value can we connect it to? We see that Na2O becomes 2Na and half of an oxygen. Now what does this actually demonstrate? We have a compound splitting up into its elements. Now one thing we need to keep in mind is enthalpy change of formation for sodium oxide. Now the definition for this is that 1 mole of a compound that is formed from its constituent element. Therefore, we see a compound formed from its constituent elements. What does that mean? You might be asking. Well, obviously, our first step in the reaction links to this. So we have a value of minus 416 for the first bit. And that removes one of our values that we need to work out. 4, 1, 6. So that's our one value, 416. So now we can check this off. So now we go to our next stage. We see that our 2Na plus half oxygen are in a solid form and a gas form. Now these, we see that our oxygen does not change. However, our Na goes from a solid to a gas. Now this occurrence can only happen via atomization. Now, atomization is when 1 mole of a gas atom is from its standard state. Normally you find Na in a solid form, but thanks to the process of atomization, we're able to get a gas. So now we have to look at which one we actually require. We require that the Na becomes atomized. Therefore, we can easily connect this to our dark blue value that we have, which is here. And we see that that value is 109. Yeah, but now we also have to take something else. They said for 1 mole, whereas we have 2 moles. So that means we will have to do 2 times 109. Which is 218. So here we'll now have 2, 1, 8. So now we already have 2 values. We can cut this off very easily. Now we only have 4 more left. So now we don't see atomization because both are still gases and this hasn't changed, nor has this changed. But we do see that this is now a plus charge and we have 2 electrons that come out of it. Now, go back to year 1 topics, and we all know that this has to link to ionization. So if we link it back to ionization, we should know that the definition of ionization is that 1 mole of a gas is formed from its ions. So if that's the case, we know that this value here must link to this. Now we know that the value here we have to get is 495, but remember this is all based on 1 mole. Therefore, if we have 2 on our hands, we'll have to go back to here. We have to do 495 times 2, which equals 990. Which means that our value here should be 990. Let's try to fix that out to at least make it somewhat understandable. 990. So now we have 3 values. We have our minus 416, positive 218, and positive 990. So our next step now, we see that the change here we have is that half O2 becomes 1 O2. Now this links back to atomization, because we only want 1 mole. And right now we have half of an O2. So now we know that it's atomization, we can link it to the enthalpy change of atomization for oxygen. So, meaning that our value here should link back to here. So now let's work that out. Very easy maths, if I do say so myself. We only have 1 mole. Therefore, we can implement the value here of 2, 4, 7. Now, we see that we have an arrow drop down all of a sudden. This shows that we are actually losing an electron. it's going back into the oxygen and becoming a negative, meaning that we're finally getting an electron affinity. Now you might be wondering, what is an electron affinity? So before we had ionization, electron affinity is basically the opposite of ionization, because this time instead of losing electrons, we're adding electrons in. So as we see, this is only one electron being lost, so it's definitely the first electron infinity, meaning that our value here should be minus 1, 4, 1. Now we have our last step in the equation. We have lost our minus E value. So you might be wondering, what is our minus E value? Well, obviously we just had our first electron affinity of oxygen. All our boxes have been ticked off, leaving us only with second electron affinity, meaning our last value has to be here, which is 7, 9, 1. And here we've already completed a Haber cycle, a Born Haber cycle. We've got all our roots solved, allowing us to calculate our direct root, which was impossible. Therefore, now we've done question 1, and it should be correct. We move on to question 2. So now the question is that they want to use the Born Haber cycle to calculate the lattice enthalpy of sodium oxide. Now the tip is that you want to follow this big arrow here, because this is essentially the answer that we want to find. Now to do this, we need to follow it, of course. So let's pick a different color that can help us with this. We want to go down. We want to make Na2O from 2Na and O2 minus, okay? So firstly, we need to go down. So what happens when we go down? In the Hess cycle, we know that the sign will become negative if it was positive, or positive if it was negative. So here are 7, 9, 1 becomes negative. Now we see that this arrow is already pointing down, so this sign stays as is. It's already in the perfect condition, we don't have to worry. Now we have 2, 4, 7. The arrow is pointing up, we need it to go down, which means minus 2, 4, 7. We have another arrow pointing up, which we have to make go down, meaning minus 9, 90. Now we have another arrow pointing up, but we need to go down, which means minus 2, 18. And lastly, we have an arrow already pointing down, and that gives us of minus 4, 1, 6. So as you see, through all the indirect routes we went, we were able to calculate an enthalpy value, a lattice enthalpy value, for the impossible roots here. So now if we add it all up, the answer we should get should be minus 2, 5, 2, 1. So now let's compare that to the actual masking. For question A, they wanted you to show the atomization, which we have. Here we go. They wanted us to show the ionization, which we have. And they wanted to show us any other 2 correct enthalpy changes, which we have. All of this was correct. So obviously here, we would have got 4 marks. Now, they also wanted us to calculate the values. So we had minus 791, which we did change over here. 141, which we changed over here. Minus 247. minus 990, minus 218, minus 416. And then once we do all of this, we see we get the value as we showed above, 2521, and we get 2521. And really, that's how simple the Haber cycle is. It's basically just a really long way of doing the normal Hess's law cycles, but without all the extra calculation. It's basically just following the path or not following the path. Either way, it's quite simple, and I believe that it's really possible if you just practice. So now lastly, I'd like to thank you all again for watching. It's really helpful when you guys watch this, and it just helps me to keep making videos on it. If you guys did enjoy, drop a like and share the video. It always helps. It always pushes me to keep going on, so on, so on. Subscribe for more chemistry content and possible maths in the future. Comment if you're confused about anything regarding this, because I'll be happy to help anyone who comments in the comment section regarding this topic, or if you find the other topics difficult, you could also comment for the future topics that you would like me to cover. Now again, thanks to all the comments that have actually come to help me to improve this video, so that I can understand what mistakes I'm making or how I can make it more clearer. And with that said, I'd like to say bye, and I'll see you all again next time.